Hi everyone, my name is Pierre Giovagnoli and I'm going to present the latest project of our research team, ADESIT. ADESIT is a visual exploration tool to help you assess the feasibility of a supervised learning project via counterexample analysis. To demonstrate ADESIT, we will take an example from a problem posed by an hydropower company we work with. We were asked, can we predict the power produced by one of our turbine up to 1% in precision? The question was not to directly produce a model, but rather to evaluate the feasibility of the project to maybe fund a larger machine learning project later. So, rather than training top-notch models to find the best accuracy possible and give it to them as it is, one of our exploration leads was to use ADESIT. The goal was to give them indicators, but also visual clues to discuss with them the current state of the problem and what they could do to improve the project feasibility. This data comes from 10 years of recording up to frequencies around a second. We will work on 1000 randomly sampled rows for visual clarity, but results are consistent across all the data. Firstly, we can directly set the target. We want to predict the power produced by the turbine up to 1% in precision. 4 potential features are provided: the flow of the river, the elevation, the blade's position, and the valve opening. From discussion with domain experts, it is known, at least theoretically, that the power is completely defined by the flow and the elevation according to the following formula. Nonetheless, due to multiple factors from turbine wear and tear to sensor uncertainty, the real-life phenomenon is very likely to deviate from this model, and their goal with this machine learning project is to get a model closer to reality. This is why we need to verify if the flow and the elevation provide good results, but also if the additional attributes could play a discriminant role in the learning process. Let's begin by observing how the incoming flow relates to the power. If the curve shows an encouraging behavior, they estimate the flow rate using reference tables with a relatively poor precision of 5%, which was known from the beginning to be a potential issue. Let's launch the analysis. ADESIT is made of 4 areas. The first area that we just used allows to upload a dataset and choose the problem settings. A second section provides counterexample indicators, and notably the G3 indicator, which acts as an upper bound on the accuracy of any model. A third area proposes an interactive dataset exploration through a color-coded table and a mirroring 2D scatter view. Both views can be used to select a tuple, which can be analyzed independently in the 4th section. This last section allows to explore the counterexample graph of the tuple selected. Note that enumerating all counterexamples is quadratic in the number of tuples, and computing the G3 indicator is an NP-hard problem similar to the minimum vertex cover. Therefore, many optimizations are applied in ADESIT to speed up the process. In that case, we see that the indicators are very low, with a prediction accuracy of at most 14%, suggesting the presence of a lot of counterexamples all over the dataset. For example, all those highlighted tuples are counterexample with the one selected. Due to the large uncertainty, tuples are in contradiction almost everywhere on a wide range of the flow, meaning that this attribute might be almost useless in practice to predict the power. By analyzing the second theoretical attribute, the elevation known up to 1 cm, we see that it behaves better than the flow, but is not sufficient alone. By using both attributes together, and thus analyzing the raw theoretical function, we get a reasonable accuracy of about 76%, but we would like to know if the other remaining attributes could provide an improvement. If we navigate the other attributes, keeping the power on the y-axis, we can observe solid correlation with the blade's positions and the opening. Let's add those 2 attributes to the set of features. We know that the blade's position and the opening are both known up to absolute 1%. By restarting computation, we observe that those 2 attributes alone should allow an ideal classifier to reach about 23% of accuracy. It is interesting to note that those last attributes were not in the theoretical model, but can be discriminating in practice. This last section can be used to understand what information is missing. In that case, we see that the elevation could be relevant to discriminate between those 2 tuples. With the elevation, we reach up to a max 92% of accuracy, which is more than encouraging for the whole project. Nonetheless, we observe that counterexamples are especially present in the 15 to 25 MW power range, meaning that prediction in this area may be less reliable. By adding the flow once again, we only confirm that it has only little predictive power. At any time, you can change the display settings, zoom, pan, select areas using lasso or square tool, and export the data. Projection axes such as PCA are also available depending on the type and number of the features. In the end, we see ADESIT as a way of exploring data and assessing learnability in view of a dataset and a machine learning problem, but also a channel to promote dialogue between domain experts and data scientists through an interactive and intuitive visualization. Thank you for watching.